Hello everybody, welcome back. You've all survived organic and hopefully you're ready to move on. Some people would argue organic might be one of the toughest concepts in this course. Some of you did very, very well on that test. Some of you struggled with it. But again, all we can do is just, all these different topics are related but really can be done kind of independently. So if you struggled with organic, not the end of the world. We're going to come on and do a little bit of acid-base chemistry for the next 4 or 5 classes, and then we're going to finish our finish the course with our last unit, which is electrochemistry, which I think is an important place to end as we move you forward into your post-secondary studies, because some of you may end up going into renewable energy technologies, whether they're solar or wind or whatever else happens to come along. So there'll be, again, opportunities for you as you leave Bernie Custis and move on to whatever comes next for you. So I want to, as I said, just have a final kind of quick look at the environmental unit. You did the environmental ISU, and again, most of you did very well on the ISU, so I want to just come back and cover a couple of really important topics from Chapter 7, Acid-Base Chemistry, which are in the ISU unit, but we didn't really cover in any kind of detail. So part of the ISU, you did a review of what you already know from grade 10 science. In our textbook, it's on page 252 of the text, and you already did some of this, so I just want to quickly have a look at it because I think this is really critical to understanding acid-base chemistry. So what did we learn in grade 10? Well, we learned that when I dissolve things in water, right, they can either create one of 3 possible scenarios. Either the solution, something dissolved in water, the solution will become either an acid or a base or stay neutral. And depending what it is that I dissolve in the water, it will become one of those 3 things. So when I say, what's an acid? It's something that's dissolved in water that has certain properties. Right? What is a base? It's something that when it's dissolved in water has certain properties. So the properties that we look at for deciding whether that solution, that mixture of water plus something is an acid or a base, include, because we do so much cooking with acids, like lemon juice, vinegars, balsamic and other types of vinegars, all kinds of things, maybe adding wine to what we're cooking, right? Different acids will add different flavors or different tastes. So when I'm looking at comparing acids and bases, right, our acids are things that taste sour. Again, think lemon juice, right? You get it, if you took a bite into a lemon, your eyes would go, wow, and your eyes would start watering, right? Really sour. Right, that's different than bitter, right? We don't use bitter in cooking because bitter is not an enjoyable sensation. Bitter is almost like if you could imagine having a bar of soap in your mouth, or if you're washing your face or your hair and you end up with a bit of soap or shampoo going in your mouth. It's got that really kind of yucky taste. That's bitter, and that's what a base is. I know that if I'm talking about the solution and I've got it on my fingertips, if it felt wet like water, acids feel wet like water. And you think, well, of course, because it's in water. But bases don't just feel wet. Bases feel actually slippery. If you could imagine taking a little bit of dish soap and putting it between your 2 fingers, your finger and thumb, and kind of rubbing them back and forth, there's a very big difference between having a drop of dish soap between your fingers and how slippery it is, and having water between your fingers. And it's still a bit slippery, but it's a different kind of slippery than we know with the bases. So I know when I'm doing a lab that if my fingers feel really slippery all of a sudden, I know that I've probably got a base on my fingers and I need to wash my hands. When we talk about acids and bases, both of them are good conductors of electricity. So when I put an acid in water, it makes the solution very conductive of electricity, and bases are also good conductors of electricity. Then we talked in grade 10 about something called pH, right? pH is a scale that goes from 0 to 14. We're going to talk a bit more about that today. And basically, if the pH is less than 7, between 0 and 7, it's going to be considered an acid. If it's higher than 7, between 7 and 14, it's going to be a base. And if it's exactly 7, it's a neutral solution. We talk about indicators. Indicators are a way, so when I look at a solution in a beaker, I don't know whether it's an acid or a base. So if I use the chemical litmus, which often can come as drops, but usually it comes as impregnated on a piece of paper, if I look at the paper, if I dip it into the beaker on the left here, the paper will turn that pinkish color, red. We call it red. If I take the paper and dip it into the solution on the right and it turns blue, I know that that's a base. So there's my quick and easy test. And the nice thing about litmus is once I put it in and pull it out, I haven't contaminated. I haven't changed what's in the beaker. All I've done is kind of stolen a little bit of the liquid to use as my indicator whether it's an acid or a base. So that's kind of the nice thing about using litmus to test. Acid is pink or red, bases are blue. B for B, bases are blue. If I look at the other indicator that we use, it's called phenolphthalein. Phenolphthalein is a strange one because of the spelling. It has a silent pH in it. Again, we'll look at the name in a minute. But notice that if I drop it into the beaker on the left, which is an acid, no color arrives. If I take it and drop a couple of drops into the beaker on the right, which is a base, it turns that bright, intense pink color. Right? So there's a quick and easy way using an indicator, which is called phenolphthalein. Again, so don't pronounce the pH, pretend it's not there because it's silent. So it's phenolphthalein. And it's colorless in an acid, pink in a base. The litmus was red in an acid and blue in a base. Now, when I look at some of the chemical properties of acids and bases, I know that if I add an acid to a metal, it will react with the metal to produce bubbles of hydrogen gas. If I add a metal to a base, nothing happens. So again, so I can see here in the test tube on the left, I've added one acid, which is very reactive, one metal, which is very reactive with the acid. You can see it bubbling away like crazy. The second one from the left is bubbling a little bit. It's reactive with acid, not quite as much. Right? The third one from the left, you can see little bubbles there. And then the one on the right, there's just kind of the one bubble forming. It's reacting, but it's a very slow reaction. But in all of these cases, I've got a metal reacting with an acid called hydrochloric acid. Right? So those are different reactions of metals with acids. And again, they produce bubbles of gas, which is hydrogen gas. The other one that's a reaction is if I add something like a carbonate to a metal. The carbonate with a metal will produce carbon dioxide gas bubbles. If I add the carbonate to a base, I get no bubbles. I get no reaction at all. And then lastly, I know that if I end up with a strong acid, it will eat away at biological material like my skin, like my cells, tissues. So that includes tissues like paper, like fabric, like cotton and wool. Right? All those natural tissues and fibers are destroyed by acids. They're also destroyed by strong bases. So very strong acids and very strong bases, we say they're corrosive, right? They will eat away at tissues and at metals. Okay, so if I move, so there's our kind of review from Chapter 7. In the ISU that you've already handed in, you answered all these questions here, right? So we've done all this, and we looked at some of the things that you've already done that chart that I just did also. And again, that's a really good review from grade 10. All right, so let's move on now into identifying acids and bases. So if I give you a chemical compound, so we know what some of their properties are, but how would I recognize it chemically? Right? How would I know what it is? So if I want to identify something as an acid or a base, it turns out that I can probably name, I don't know, I'm just guessing, probably say 200 different acids and probably maybe 40 or 50 different bases, right? But there are ultimately thousands and thousands of all the above. And the one thing that we see very common with acids, not always, but I would say almost always, for our case it'll be always, is if I see that there's an H as the first element, right, that tells me that it's probably an acid. Right? So all of those things that start with H, note the last one, HC2, this one here, HC2H3O2, it also has H's in the middle, but I'm not concerned about those H's. I'm only concerned with the H that comes at the front. Now this molecule here, I can see it has 2 carbons, 2 oxygens, and it has 4 hydrogens, 1 at the beginning and 3 in the middle. The one at the beginning has very different properties than the 3 in the middle, which is why it's been separated from them. So as soon as I see a compound that's got an H at the beginning, if I'm talking about, if I give you this compound here, HCO3, I know it's an acid right away because it's got the hydrogen at the beginning. Okay, that's carbonic acid. That's just H2CO3, sorry. H2CO3. So, anything that starts with a hydrogen is going to be an acid. Typically, not always, but typically, our compounds that are bases have a hydroxide group in. Remember the OH from, the organic unit. But when I see a compound that has a hydroxide, hydroxide is an ion. Remember from earlier in the course when we were learning to name compounds, hydroxide is an OH -1 ion, right? And it forms ionic compounds as a negative ion with positive ions, which are typically metals. So I can see here that I've got a number of different, there's sodium hydroxide, potassium hydroxide, this is a strange one, this is ammonium hydroxide, and then the last one is calcium hydroxide. Notice that they're ionic compounds, so I don't need the dihydroxide, because in ionic compounds we don't use the mono-di-tri, we just calcium hydroxide. Now going back historically, what gives these compounds, this one and these ones, what gives them their properties, right? And a chemist named Arrhenius, going back several hundred years, proposed a theory of what makes an acid and what makes a base. And according to the Arrhenius model, which is very close to what we choose today, it says when I take an acid, like hydrogen chloride or hydrochloric acid, or hydrogen nitrate, which is also called nitric acid, when I put them in water, they ionize. Now remember that word ionize means that the ions that are in the compound, in the ionic compound, will separate. Water will get in there between the H and the Cl and pull them apart, so the H comes off the Cl, but the Cl has got such a high electronegativity, remember from our organic unit, that it actually steals the electron from the hydrogen, and I end up with a chloride ion and a hydrogen ion happening. The same thing here. The water gets up in here between the H and the NO3, and the H gets popped off as a hydrogen ion, and the NO3 goes off as my nitrate ion. Right? So that's what Arrhenius says about an acid. So when I put it in water, right, it will ionize in water to produce hydrogen ions. Arrhenius also said bases do a similar thing. It's that when I put them in water, water is going to dissociate them. They're going to separate the ions, and basically it's going to get up here between the sodium and the OH, and it will separate the sodium ion from the hydroxide ion. And notice I've got the AQ here to show that they're floating around in water separate of each other. The same thing here, the calcium hydroxide, water gets up in between the calcium and the hydroxide, and I end up with a calcium ion, and the hydroxide ions have been freed up from the calcium hydroxide. So whenever I put a base and dissolve it into water, it dissociates the ions. It separates the ions, right, into hydroxide ions plus whatever the metal was that was associated with that ion. Okay, so there was Arrhenius's model for acids and bases, and part of this was, it kind of aligns with what we talked about in that big chart up there. It's because we know that acids and bases are good conductors of electricity. That happens because I have charged particles floating around in the water. In other words, I have the ions floating around in the water. And as they are floating around, they will help to conduct the electricity through the solution. Remember, electricity is the movement of charge, the movement of electrons through matter. So if I have charged particles in my water, it makes the solution a better conductor of electricity. So both acids and bases now become good conductors of electricity, and we know that if we go all the way back up here, that if I look at electrical conductivity here, acids conduct electricity and bases conduct electricity, right? And the reason for that is because of the ions that are released in solution. Now the one main problem with the Arrhenius theory, one of them, not all of them, but the main one came from first this compound here. When I put this solution NH3 ammonia, which we use for cleaning our windows, it's in Windex, it's in other types of household cleaners. If I put it in water, the pH comes out around pH 11. You think, well, hang on, there's no OH here. How could it be? pH 11 tells me it's a base right off the bat. How can it be pH 11? How can it be a base if it doesn't have a hydroxide ion? So it turns out that a bit of a funny thing happens when I put ammonia in water. What's going to happen is the ammonia is going to see the water, and it's actually going to split the H off the OH here. It's going to steal a proton from water to make it NH4+, and that will leave an OH- to come off as the hydroxide. So I'm still going to get my hydroxide being produced, even if it wasn't in the original compound. Now the other problem that we have with the Arrhenius model of acid and bases is what happens when I put hydrogen chloride in water. Now, if I put hydrogen ions into water, if my HCl separates, that to produce H plus and Cl minus, that's what Arrhenius says, right? This is going to produce H plus and Cl minus. But the problem is that H plus here that's being produced can't float around in water very easily, because as soon as it sees the water, it's going to bind to the water. Oops. It's going to bind to the water, right? Remember, the water has a partial positive and a partial negative bond on it because of electronegativity, right? The electronegativity of oxygen is so much higher than water that H2O actually has a positive end and a negative end. Okay, so the oxygen here with a high electronegativity is sharing electrons with hydrogen, and it pulls those electrons towards itself, leaving the hydrogen end of this bond a little more positive and the oxygen end of this bond a little more negative. Same thing happens over here. This oxygen is sharing a pair of electrons with hydrogen, but oxygen has a high electronegativity, so it pulls the electrons towards itself, meaning that this end of the bond is a little more negative, this end is a little more positive. So what I now have is H2Os always look like this, because part of the reason for water having its unique properties, it's part of the reason why there's life on this planet. Now, if I take my HCl here and I separate the H from the Cl in water, what's going to happen is that H plus that comes off is now floating around, and it sees the very negative side of the oxygen here, and it says, I'm not prepared to float around on my own. I'm going to stick myself right on here, and I'm going to help to form a new ion. So this is what happens. I end up with an H3O, but because I added H plus to an H2O, the H2O becomes H3O, but it has the plus charge that the hydrogen ion had, and it ends up producing this thing called H3O plus. H3O plus is the new molecule, the new ionic compound, polyatomic ion, that we're going to see, and it's called hydronium. So Arrhenius was kind of right that the HCl will separate into an H plus and a Cl minus, as we're seeing up here, but it turns out that that H plus, as soon as it sees water, it's going to jump onto water and form an H3O plus. So what's really happening in this solution is when HCl, when the HCl it dissolves in water, it's going to form an H3O plus and a Cl minus. So water becomes a reactant in this process. right? Because again, I'm using the water to pick up the hydrogen ion that came off the HCl. So Lewis came along and modified the Arrhenius model, and he said, okay, how are we going to change our definitions now so that it actually works? And Lewis gave me a new definition for an acid, and he said an acid is something that reacts with water to produce hydronium ions. Okay, there it is up there, the hydronium ion, H3O+. So that's what an acid is. Because remember before, Arrhenius said all H-containing compounds will produce H plus the negative ion. And now Lewis is saying, well, the H plus doesn't really exist on its own. It actually has to couple to water, to the O of H2O, to make an H3O plus. And bases are things that when they dissolve in water, they will release hydroxide ions. Even if they don't have hydroxide ions, right, they will release hydroxide ions. Now, the way that that's going to happen, just like ammonia did, is it's actually going to create a hydroxide ion, an OH minus ion, using the OH minus that was in the water. Oops, that was in the water. So, like I said before, there are thousands and thousands of different acids and bases. Right? They're all over the place. They're in so many different things. They're in our food. They're in our cleaning products. They're in our materials that we have around us in our homes. All of our pharmaceuticals, right, are either acids or bases. All right, so it just goes on and on. Anything that will dissolve in water will usually produce either an acidic solution or a basic solution. Now, so 7.1 here looks at some of the common things that we might find in our homes or in our workplaces. Right, so the first one here is ammonia, NH3, nitrogen trihydride. As we just saw a moment ago, it's a base because it rips protons off water to release OH minuses from water. So even though it doesn't contain OH minus, it's going to be a base. And again, what is ammonia used for? Outside of our homes, it's used in fertilizer. It's used in the production of a lot of synthetic fibers, all the things that we talked about in the organic unit. It's used in the production of explosives that are used for mining, for putting in new roads, for blasting, and probably even for artillery. So again, a lot of uses for ammonia. We've got hydrochloric acid, HCl, which, as the name suggests, would be an acid. And again, it's used in a lot of our food substances. It's used in the rubbers and plastics industry. It's used in mining. It's used in photography, production of photographs. And in a lot of the different textiles that we use acids for. We saw that in the organic unit for esterification reactions and for elimination reactions. We use acids also. We also use it for refining ore, so it's used for part of the mining industry again. And if you work in a lab of any sort, whether it's a foods lab or a medical lab or a hospital lab or a pharmaceutical lab, you're going to be using acids all the time, such as HCl, hydrochloric acid. We've got a chemical, it's called lime. It's not about the lime that grows on a tree. This is a white powder, white crystal that looks a bit like table salt. And basically what it does is when it sees water, it will react and strip protons off the water to produce hydroxide ions. And again, a lot of farmers use calcium oxide or lime. And even gardeners sometimes will, if their plants aren't doing well, and the garden center will say, can you bring us a sample of your soil? We'll test it for you and find out why your plants aren't doing well. They'll say, oh, your soil is too acidic. We need to add some base to your soil. Add this calcium oxide. Add this lime to your soil, and it will neutralize the acid that's in your soil. It's used for making mortar for building. It's also used in construction. And it's used, again, in some of the power plants and in mining processes that release sulfur dioxide. It's a way to try and get rid of the acid that's going up as acid rain. So it's a base. We've got phosphoric acid. Again, notice the H at the beginning there. So So again, we've got three acids here. The first one was HCl. The second one is H3PO4. The third one is H2SO4. Again, notice what they all have in common, right? All starting with H. Makes them all acids. Phosphoric acid's in a lot of different soft drinks, a lot of colas, root beer, lots of different things have phosphoric acid added to them. It's used in detergents, like laundry soap. It's added to fertilizers to make your plants grow better. It's used in the dental industry when they are filling cavities. Right? So again, lots of uses for phosphoric acid. Sodium hydroxide is a common one that we find in our homes. It's used for cleaning our drains. If we have a plugged drain and you buy some Drano or Liquid Plumber or some other type of drain cleaner, you pour it in, you come back an hour later and your drain is clear. It was probably sodium hydroxide. It's also the element. It's also the compound that comes in oven cleaners that we use for cleaning our ovens. Sodium hydroxide is used in a lot of synthetic processes, such as the production of soaps, production of plastics, production in the pulp and paper industry. And then also it's used in oil refineries. It's used in, we haven't talked about fracking, I'm not going to, and the treatment of water. All right, and then the last one on our list there is sulfuric acid. Sulfuric acid is sometimes called battery acid because it's in car batteries. It's H2SO4. I see the H at the beginning. It tells me that it's an acid. And again, it's used in a lot of different industries, pharmaceuticals, explosives, dyes, and on and on. Paper, soap, detergents, plastics, used in oil refineries, used in processing of metals and metallurgy. So lots and lots of applications for these acids and bases. So you can see why this chemistry is so important, regardless of which type of industry you're getting into. Okay, now when I talk about acids and bases, we often think about acids and bases as being really good or bad things, but really we're often talking about what we call the strength of the acid or base. Now, the strength isn't really talking about how concentrated the solution is. The strength talks about when I put it in water, how effective is it at doing what we just said? In other words, how effective is it? If my acid is a generic acid, so I'm just going to call it HA, so it can be any acid, starts with an H, so I'm going to put the H at the beginning, and A for whatever comes after that. And we know that it reacts with water to form the hydronium ion, and then the negative ion that came from the acid. Now, that being the case, when I put that HA in water, sometimes the acid will find the water, and every HA that's put in there is going to become an H3O+. As soon as I put it in water, this is going to go to here immediately. That's called a strong acid because all the HAs will dissociate. All of them will become hydronium ions, the H3O+ hydronium ion. Okay, and those are strong acids. And some examples of strong acids include hydrochloric acid is a strong acid, and HNO3, called nitric acid or hydrogen nitrate, is another strong acid. Most of the acids in the world, I'd say of the, if I could name 200 of them, 195 of them are not strong acids. They're called weak acids. Right? And weak acids are ones that when I put them in water, only a very small amount of this goes over here. Most of it stays here unreacted with the water. Right? Less than 1% usually, sometimes 0.1%, which means 99.9% will stay here and 0.1% will go here. Maybe 0.01 will go over here and 99.99 stays over here. Right, so the majority of my acid stays as the acid form, not as the dissociated form. Those are called weak acids. So an example might be this one here, and I'm not sure what that is. I'm assuming that it's vinegar. It's acetic acid. Right? So when I put acetic acid in vinegar, 99% of it stays like this, and 1% of it will dissociate to release hydronium ions. Okay, and again, notice that most of the acids in the world are weak acids, which means when I put them in water, they will stay as the acid and not dissociate to produce the hydronium ions, the H3O+ ions. So if I look at what some of the strong acids are, there's only a small number that we need to consider, and really there's two groups, right? The first group are the halogen acids, right? Bromine, chlorine, and iodine, but not fluorine. So hydrogen bromide is actually called hydrobromic acid. Hydrogen chloride is actually called hydrochloric acid, and hydrogen iodide is called hydroiodic acid. Right? So those three halogens form strong acids. When they are dissolved in water, they separate, boom, 100% to release all hydronium ions and either bromide or chloride or iodide ions. The other ones that are often strong acids are a lot of the oxy acids. Those are compounds that contain oxygen containing polyatomic ions like nitrate, chlorate, and sulfate. And the compounds are going to form the acids. Hydrogen nitrate is called nitric acid. Hydrogen chlorate, perchlorate is called perchloric acid. And hydrogen sulfate is called sulfuric acid. And they're strong acids, which means the H, all of these H's all the way down here will separate 100%, and they will add to water to form my hydronium ions. So that's my definition of a strong acid, right? That those compounds, those ionic compounds, will separate. So those are strong acids. What about bases? Which elements make strong bases? Well, there are lots of bases in the world. Our strong bases are the ones that separate in water 100%, at least 99+%, right? Maybe not 100, but it'll be 99.9 or 99.999%, right? Basically 100%. So those are the group 1 metal hydroxides and the group 2 metal hydroxides. Now again, if I look at my periodic table, okay, remember my group 1 are over here: lithium, sodium, potassium, rubidium, and my group 2s are beryllium, magnesium, calcium, strontium. So these hydroxides will be strong. These hydroxides will be strong. Scandium hydroxide, no. Titanium hydroxide, no. Zirconium hydroxide, no. Iron hydroxide, no. Rubidium hydroxide, no. Right? They're all weak hydroxides. Right? Cobalt hydroxide. If I scroll down the other side, if I look at nickel hydroxide, copper hydroxide, zinc hydroxide, mercury, gold hydroxide, right? All those hydroxides will be weak bases. So the group 1 and group 2 metal hydroxides and the group 2 metal hydroxides are all strong bases. All the rest are weak bases, which, just like the weak acids, when I put them in water, they don't separate very much. So if I gave you a solution of copper 2 hydroxide, the calcium hydroxide will separate 100%. This won't. This will stay mostly as copper 2 hydroxide floating around in water. Right? It will not dissociate. It will not separate into copper ions and hydroxide ions. Okay, so those are how we decide whether acids and bases are strong or weak, is how much they follow the definition. How much will they produce either hydronium ions in solution, or how much will they release hydroxide ions in solution. Right? And those are strong acids and strong bases, weak acids and weak bases. Now, the other thing that we can talk about is how many moles per liter are there. Sorry, we're going back to chapter 5 and 6 here a little bit. So we're going to have to, for part of this unit, get our calculators back out a little bit and talk about how many moles there are dissolved in a liter. So I can take a small amount. Again, think about a coffee, right? Putting some people just like a tiny bit of sugar in their coffee. Some people put a spoon. Some people put 2 spoons. Some people put 3 spoons. Right, the more coffee you put in, you know how it affects the flavor of the coffee. The more sugar, you put in. And the same thing happens with solutions. I can put a certain amount of sodium chloride in water, and it'll give me a certain concentration or solution. If I measure the amount that I'm dissolving in moles in how much liquid that there's going to be, it will tell me how concentrated the solution is. And we talked concentration before, C equals N over V. Right, concentration talks about the number of moles dissolved per liter, N over V, number of moles over volume. Right, so there's two ways to talk about acid and base in solution. One is, do we have a strong or weak acid, or strong or weak base, and how concentrated or dilute is my acid or base in the solution. Okay, so I'm just going to finish off. Again, most of this you've already seen before, so I don't think there's too much new yet. Well, I shouldn't say that. This was all pretty new about the hydroniums and the hydroxides. I want to come back, though, to pH for a minute. So when we're talking about pH, again, this is all review. The pH, basically now that we have a definition for acids and bases, if I say, what is the pH telling me? It's telling me either how much of this is in the solution or how much of this is in the solution. If the pH of hydronium ions is quite high, if the concentration is high, the pH will be very, very small. Maybe pH 1, pH 0, pH 2. If the hydroxide ion concentration is very high, the pH will be quite extreme, either pH 11, 12, 13, 14. Right? So the pH now becomes an indicator of how much of these ions are present in my solution. Now I know that it turns out that in all solutions something is dissolved in water. Water is a weird chemical, right? Water, when I put water into a beaker, some of the waters that are in there, okay, and again, not all of them, but a very small amount of these will react with other waters, so that one H2O here give myself some room to work here. One of the H2Os and another H2O, right, are all in solution. Sometimes one of the OHs can steal the hydrogen ion from the other one. And what that's going to do is it's going to create this compound here. Because the H here comes as an H plus ion, leaving the hydroxide minus, what I end up with is an H3O plus being produced and an OH minus. You think, how can I have H3O plus, which is an acid, and OH minus in a solution if I didn't put anything in the water to begin with to produce those things? Well, water has the ability on its own, without anything even added there, to produce some hydronium plus hydroxide. But notice that every time one of these is made, one of these is made. Right? So what turns out is the number of these will be always equal to the number of these in water. Right? The number of these has to be equal to the number of these, because when one of these is made, it makes one of these. If 50 of these are made, 50 of those are made. If a billion of these are made, a billion of those are made. Right? So what that means is, because there are equal amounts of both the hydronium and the hydroxide, that makes for a neutral solution. Right? The neutral solution, we know, has pH 7, right? And we know that now, we know the reason why it's neutral is because there are equal amounts of the acid compound, hydronium, and the base ion, hydroxide. So the hydronium ion and the hydroxide ions are there in equal amounts, and that means that the solution is going to be neutral. Okay, equal amounts of hydronium and hydroxide. If I have a solution that's an acidic solution, notice I added something like HCl to my water. Right? The H is going to ultimately come off and ultimately create a bunch of H3O pluses by reacting with water, but it doesn't create hydroxides, right? The H plus just tacked itself onto some H2Os to make H3O pluses. So now I've got more of this and less of this, and by definition, that's what creates an acid solution. And according to our number scale, a pH which is below 7, between 7 and 0, is going to be acidic. And the further I get from 7, the higher the concentration of hydronium ions. So pH 0, which is the highest pH, the lowest pH, means the highest concentration of hydronium ions possible. And that's a concentration, again, remember, all the way back to wherever it was C equals N over V there, the units here are going to be in moles per liter. Moles of hydronium ion, H3O plus, per liter of solution. And then if I look at my solutions at our bases, they're the opposite. I know that the pH is going to be greater than 7 for a base, and the reason why is when I put the base in water, it's either going to release hydroxides or steal OHs, steal hydrogen ions from solutions to produce hydroxides. Because there are now way more hydroxides than hydroniums, it's now a base, and the more hydroxide there are, the closer the pH gets to 14. And again, notice that we're going to measure our concentration of hydroxide ions, in moles per liter, just like we did up here for hydronium ions. Okay, now the thing about the pH scale is it's called a logarithmic scale, which means every pH unit means 10 times more. So if I had looked at a solution that's pH 3 and another solution that was pH 2, I'd say, oh, they look like they're pretty close. One's 2, one's 3. That's pretty close, right? 2 to 3. Well, it turns out that going from 2 to 3 means 10 times more. Well, actually going from 3 to 2 means 10 times more acid, 10 times more hydronium ion. 10 times more hydronium ion. If I go from pH 2, if I change by 2 pH units, so it's 3 compared to 4, right? Because there's only 1 pH unit difference, it's 10 to the 1, which is 10 times. If the pH, comparing a pH 2 to a pH 4 solution, I got 2 beakers in front of me, one's pH 2, one's pH 4, the one that's pH 2 has 10 to the 2 times more because there's 2 pH units difference, right, between the two. And if I look at pH 12 in one beaker and pH 9 in another beaker, I say, how are they different? The pH 12 has more hydroxide ion, right, but because it's 3 units higher, right, pH 12 versus pH 9, it has 10 to the 3, which is 10 times 10 times 10, or 1,000 times more hydroxide than pH 9. So you can see that with a scale that goes from 0 to 14, I can talk about a huge range of concentrations of hydronium and hydroxide ions. And then it turns out that as I look at the concentration of one, I can also know the concentration of the other, because the two of them are related to each other directly because they're both present in the water-based solution. And it turns out as one of these is a higher amount in the solution, the other one is at a lower amount in the solution. The higher the H3O plus, the lower the OH minus. The higher the OH minus, the lower the H3O plus. So there's a relationship between those two that says if I know one, I know the other. Skip that. Okay, so if I want to measure the pH, I can use pH paper, which is a piece of paper that I dip into the solution. It's kind of like the litmus we saw a moment ago, but it will basically tell me what the pH is of that solution. Or we can use something called a pH meter. pH meter has a little glass probe with a little membrane at the end of the glass probe, and when I dip it into my beaker, it will just say, oh, 10.7, that's your pH, or 3.6, that's the pH, or 7.3, that's your pH, right? So I can either use a pH meter or pH probe to measure the pH of a solution, or I can use pH paper, and the pH paper actually has a range of colors, and the different colors tell me about the different pHs. The other possibility would be to use just a simple acid-base indicator like the ones we had in our table. The first one was litmus that we talked about. I showed you the picture earlier. The other one was phenolphthalein, and most of these typically have only 2 possible colors. Right, one represents an acid, the other color represents a base. So for litmus, red is an acid, blue is a base. For phenolphthalein, colorless is an acid, and pink is a base. And if I look at pH paper, let me just see if I can pull up a quick image here of pH paper. I'd forgotten I was going to get to this. I would have downloaded the picture earlier. Oh, that's not what I wanted to do. I downloaded Google Maps. Okay, so if I look up pH paper, so when I dip it into my beaker, it will come out a certain color, and the color can be compared to a reference color system. So I don't think they're not showing it. Okay, so here's an example here. So when I dip my piece of paper into the solution, it'll come out a certain color, and you can see that the color goes from red is pH 1, a little less red, more orangey, going to pH 2, pH 3, pH 4, turning more mustardy color, pH 5, 6, getting into the greens and darker green, pH 7, 8, darker green 9, turning more into the blues, and then finally you could just see that the other ones in this photo, they don't look very clear, but they're a lot clearer on the actual device that we use to measure. So there's one possibility, and then the other one would be using a pH meter. And the pH meter has got a probe like this one here, and you just dip the probe into your solution down there, and then it will tell you what the pH of your solution is on a digital scale. So it's nice and easy to use. You dip it in, it tells you the answer. Right? So those are different ways to measure pH. Okay, so that basically finishes up our first note on acids and bases. I'm going to leave you with some homework to work on here on page 264 in our textbook, and then tomorrow I'm going to come back and talk about neutralization reactions, which are what happens when I react an acid and a base, and we're going to see what the result will be from that type of chemical reaction. All right, so if you're still listening to this long video, I sent you a remind message about getting into the school. If you really want to get into the school, if you've got anything in the school that you want, all right, next week is your chance to get it. If you look in the hub, I've given you instructions. There are 2 documents you need to look at. Read them very carefully. Right, there are 2 days for people whose names start with A to G, last names. There are 2 dates for people whose last names start with H to O. And there are 2 days for people where the names are from P to Z. You have to book a time, and you will get a 15-minute time slot when you can go into the school to get your stuff out of your locker. Or if you know you've left something in a classroom, you have to email the school and let them know the instructions are all in the documents I left you. All right. If you don't pick your stuff up now, you may not get them. All right, because typically in the summer, somebody goes through and empties all the lockers, everything goes